going to talk about Bluepass, an indoor Bluetooth-based localization system for mobile applications.
Well, good morning. Like the chair said, my name is Javier, and I'm going to present an indoor Bluetooth-based localization system for mobile application called Bluepass. This is the summary of our presentation. I will first start with a little background about localization concepts, and then I will move forward. So, the main goal of the Bluepass system is to provide a location-based service, which is basically a service that can be provided to any mobile device which is connected to a network using its geographic localization. So the two main location-based service can be the outdoor localization service, such as GPS or wireless sensor networks, or the indoors one, which uses some different technologies, such as Bluetooth, wireless LAN, or radio frequency ID. So, one of the most famous techniques to actually perform a localization is the trilateration or multilateration techniques, which consists in several circles intersections. So those circles are based in the distance between a base station and a mobile device. So when the base station detects a mobile device, it creates a circle based on that distance, and the intersection can provide a probable area, or more likely, a probable point where the mobile device is going to be located. However, in order to know the distance between the mobile device and the base station, we need to use a propagation model, in our case, an indoor propagation model. The main objective of a propagation model is to define or to describe the communication range of a base station, and to model the environmental dynamics, which in an indoor environment, there are laws of dynamics. So in this paper, we focus on the International Telecommunication Union's indoor propagation model, which is described by that formula. A little explanation about the formula. The L is the path loss, or the signal strength. F is the frequency which the system operates. In our case, we are using Bluetooth, so it's 2.4 gigahertz. And the N is an attenuation constant that depends on the environment that the system is deployed. D is the actual distance between the mobile device and the base station. And PF is a function that defines the path loss between floors in case that the system is deployed in a building with several floors, which is not our case. We are working in just one floor building. So, the most common location problem approaches are the ones that are based on the radio signal strength indicator. Those techniques use the signal strength with propagation models to estimate the distance, and then another technique such as trilateration, for example, in order to find the coordinates of the mobile device. Fingerprint-based solutions are another approach that actually makes some previous measurements on the environment and create signal maps of all the environments according to the several base stations. So once a mobile device is detected, it checks the database and consults the most probable location according to the database and the signal maps that were created by the previous measurements. Another technique is the radio frequency ID based solutions. Those are quite similar to the other ones. The only big difference is that they don't use like Bluetooth or wireless. They use radio frequency tags, which is a special hardware. The main drawback of that kind of techniques is that the cost of the system increase because they need to use specialized hardware. So now we'll talk about the Bluepass system. Once the Bluepass system is deployed, it takes constant measurements of the radio signal strength of the mobile device within the environment where the system were deployed. So once it takes the signal strength, it calculates the coordinates for the room. I will talk more about that in the next slides. And it uses a client-server architecture. It's quite interesting because some of the main issues of localization systems is the privacy issue. So you don't want to be located, or you must have the option to choose between being or not being located. So with the client-server architecture, the Bluepass system can provide the option to log into the system in order to be tracked, or to log out the system in order to not be tracked. So you have that option, which is quite important in this kind of systems. So the architecture of the system is shown in this picture. It basically consists in a main server, which is located on the internet, and which have a database with all the users and maps informations. So the reason that the main server is on the internet is because we intend to deploy the system in several places, in different places. Like, for example, several universities. So if we want to deploy the system in 2 different universities, we can have a local server on each university connected to the main server, consulting the users and the mapped information all the time. So each local server is responsible for calculating the position of the mobile devices within that environment. And to use that, it uses several base stations, which are the computers with the Bluetooth symbol, because they have a Bluetooth adapter in order to locate the Bluetooth mobile users. And well, there are several users in each environment. So the users have obviously a mobile device which is running the application of the Bluepass system, which can be seen in this picture. So like I said, we have a login system. You have to log into the system in order to be tracked. And after you log in, you have access to the map of the building that you're located. And those numbers in the rooms represent the number of users that are in that room. Because like I said, the Bluepass system works with room level localization and not coordinate level localization. So we are interested to know which room the user is located and know in which part of the room the user is actually seated, or anyway. To do that, the room level location, we propose a method called signal density coverage method. I will explain in a few pictures, and I will make some assumptions first in order to make it easier to understand. So let's assume a 2-dimensional map, which is the building map, covered by a regular grid. Each grid cell has like, I don't know, 1 square meter size. We can change that size, but it's only an example. So let's assume that we have a propagation model that can actually convert the signal strength into the distance between the mobile device and the base station. And instead of representing the propagation as a circle, like I showed you in the multilateration slide, we are going to use a square. Why we're going to use a square? Because this is an algorithm, and the grid is represented by a matrix structure in the computer, so it's easy to propagate the signal in a square when we are using a matrix instead of a circle. So it's like a convenience choice. So this is our area, our hypothetical area. It's composed by 4 rooms and 2 hallways. We can see that in 3 of the 4 corners we have a base station with a Bluetooth, and there's a user within one of the rooms. So once the first station actually detects the user, it estimates the distance between them using the propagation model, and it increases the value of the cell within that area. It's something like this. So each cell has one station saying that probably the user is in that cell. So when we do that with all the stations, we will have found some areas of intersection. But an interesting thing about this method is that it actually exploits some information that approach like multilateration does not. So as you can see, the nearby areas of the station are not increased. Why? Because obviously the mobile device is far away from the station, so the signal that has been captured is really low. So when the signal is too low, we know that the mobile device is not nearby the station. So there is no point at all to increase the nearby cells because we know that the user is not there. So we can choose a more probable area to increase and to forget the information that we know that is sure. So if we do that with all the stations, we'll create areas with more signal density, which is more probable the user to be located. So we can see that there's an area which the 3 stations are saying that the user is probably in. But the user is not within those cells. So in order to choose the room where the user is actually located, we evaluate the room which has more cells with the higher value, so which have the highest signal density. In this case, we can see 4 cells in that room and 1 cell in the hallway. So the most probably area will be the room. So that's how it works, the system. It was only to explain. In this case, obviously it goes right, but we're going to see in the result part that it's not always that way. So, in the experimentation of the paper, we worked in an area for like, I don't know, 192 square meters, which is composed by 4 rooms. 3 of them are computer labs. It's something like this actually. 4 rooms, 3 of them computer labs, and each computer lab have a base station. Each fixed station have a Linux desktop with a class 1 USB Bluetooth adapter, and the servers are located also in the computer labs because we are not using several buildings, so it's like the same. And we use a 2-dimensional map split in 1 square meter of cells. Once again, or something like this. So, the propagation models choose to test the system were actually the ITU model that I've already explained. And we did some regressions in using data collection that I will explain in the next slide. And we also compared the results using the propagation models in the whole environment, like the full 4 rooms and hallways, and in a unique room. Because we saw some works that deployed a localization system within only 1 room. So we want to compare the difference between 1 room and a whole environment. Oh, okay. So the ITU proposed a table of frequency and attenuation constant that should be used. In this case, we can see that there is no constant for a 2.4 gigahertz frequency. So we try to choose the closest one, which is the 1.8 gigahertz, in order just to test and see the results. And then we will try to find the more appropriate constant which actually fits the area. So the data collection consisted in store several signal strength measurements, more specifically 50 samples on each grid cell. So we took 50 samples on each cell, and we calculated the average in each point, and we associate the average with the real distance between the mobile device and the base station in order to try to find a function that describes that. We actually didn't make the measurements in all the grid cells because some of the cells were unreachable regions like bathrooms or restricted areas. But most of the area was covered by the data collection. So, once we have the data and the propagation models, we have to estimate the position of the mobile user. To do that, we consider a minimum station number that must detect the mobile user, which in this case is 3. And we use tree iteration method with the ITU model. Tree iteration with a linear regression that I will show that is the best regression that we could make. And the signal coverage density method, which is only for room level location and not coordinates level. So, trying to find the constant, we use values between 1 and 100 in order to test the most quantity of constants. As we can see here, in the y-axis we have the error in meters, and in the x-axis we have the attenuation constant. So lower values have high errors, and when it's near to 30, the error starts to decrease and then start to increase after that. So in numbers, we can see that the suggested constant, or the arbitrary constant, which is 30, presented the highest error within a single room and within the whole environment. It's like 4.5 meter error in coordinates, in a single room and more than 8 meters error in the whole environment. So it's not reliable at all. It's like you're here or 8 meters away, it's reliable anyway. So we did two kinds of regression. That's a linear regression and an exponential regression, and the results I'll show it there. As we can see, the two best methods are the linear regressions and the ITU model with the constant 37, which presented the lowest errors in both areas. So we chose those two ones in order to test the actual location system within room level and coordinates. So to do that, we made a new data collection, which consisted in 100 samples divided into two groups, a 30% group and a 70% group. We did that to compare the results within a small sample and a bigger sample in order to see if the results were similar. That data collection was made in 3 different spots of each room, which means once near the door, once in the middle of the room, and once near the station. We do that to try to represent the most common case or the most extreme case that can happen. Any other case is just a combination of those 3. So we do that in the rooms that there was a station, so 3 rooms. As we can see, the coordinates error is applied only to trilateration because the signal coverage method does not calculate coordinates, so we can assume an error in meters. As we can see, the ITU model error are really like 1 meter, 1.5 meters higher than the linear regression error in both samples. So the linear regression is actually more accurate than the model itself. However, if we calculate the room level error with the ITU model and the linear model, and also the signal coverage method, the difference between the ITU model and the linear model is like 20%. So in the y-axis we can see the accuracy of the method, and in the x-axis we can see the parts of the room where the data was collected. So we can see that when the device is near the station, the signal coverage density method is like 100% accurate, because like we saw, the cells near the station are going to be increased and only within that room. So the method will know that the user is in that room. That doesn't happen when the user is in the middle of the room, because it's one of the more dynamic part of the area or the room. And well, in the average it was like 80% accuracy, which is a good value, considering that each location is done like in a 6-7 seconds period. So if you're located once each 7 seconds with 80% accuracy, is a very good result. So we did some experimental results, which is very important because we can actually prove that in a real environment the system can have a good performance. We exploit the information reliability by ignoring the fact that the lowest signal represents that the mobile device is not near the station. So the trilateration method can't do that. It's just a circles intersection. But the signal coverage density method can do that. And it's quite stable, as we can see in the results. If we use the same method with the signal coverage method with ITU or linear regressions, the results are very similar. So we don't need a really accurate propagation model in order to have good results with this method. As future works, we pretend to change the base station positions in order to try the best position in the room to exploit the fact that when it's near the station, the method is always accurate. We want to try some data fusion between the both methods, so signal coverage and trilateration, in order to find the room and the coordinate. And we intend to deploy the system in different environments so we can show similar results in different areas. Okay, any questions?
It's really interesting.
I have 2 questions. So the first is, what happens if more than 7 students are in a room? Because the maximum number of stations that can be considered in a Piconet is 7 slave nodes. And the other question is what happened with the moving students, because the time between the inquiry and the page phases in Bluetooth can be very long.
Okay. Okay. The first question. Actually, I will go back to the architecture picture, so it's more. So, actually, the stations are not connected by Bluetooth. They are connected in a local area network using the computer network, not the Bluetooth network. The only function of the Bluetooth adapter is to scan and send to the local server the information. So, in theory, we can connect like more than 7 computers in a local area network, each one with one adapter. So, it's not that case. So, if we have more than 7 students, actually we perform tests with more than one mobile user. The only reason I showed one because it's simple to explain. Within the time of a scan, that is 7 seconds, like I said, we can actually find all the users or most of the users that are in the room. So it's quite scalable, the system. So you can have really high quantity of persons in the room, and all the station will perform them, will find them. And the second question was, I'm sorry?
About the time required for the inquiry and the page phase.
Oh, when they're moving, right? Okay, actually we didn't make tests with actually mobile users. We just stand the user in a position and trying to find the error. But that's an interesting point to future works, because in a real indoor environment, people are like moving all the time. So we didn't perform tests for that, actually.
If I can add a comment, since in the past also my research group worked with solutions that are quite similar to the one you proposed. A comment and a suggestion for possible improvement could be the fact that, especially when you consider mobile devices, you can achieve higher accuracy by considering the history of past estimations of the position.
Okay.
Because of course you have a correlation due to the fact that basically one mobile device cannot disappear, so continuously move in the space, and that could help a lot in the accuracy of the estimation.
Suggestion. And considering that we have databases, that should be easier, I guess.
Yeah, definitely.
That's
definitely.
real. Thanks for that suggestion. Any other question?
I have one the relationship between RSSI and distance D. How does
I'm sorry?
they relate? You mentioned the RSSI, signal strength,
Yeah, and the distance.
and distance, how they relate.
Yeah, they're related.
Are they a linear relationship, or, if I give you RSSI, how do you calculate D?
Okay, like we said, we did some regressions. So by having the RSSI value and the distance, we can try to create a formula from that, a regression, and that the formula is going to be something like the ITU formula when you input the signal strength, and you will get the distance. So the data collection was actually to perform that formula, to calculate that formula, based on real data. So that's the relation in the regressions.
So if you have a strong signal strength, what would be the distance? Is a shorter distance or longer distance?
Shorter, because the stronger the signal is, you're closer to the station. Less interference.
Is it also depend on the environment you're
Yeah, it
working?
depends on the environment. But
If it is open environment, even if it is slightly longer distance, still you can get the good signal strength.
yeah, but considering that the area was composed by the computer lab, there was a lot of interference. So if the signal was strong, in the experiment, we can prove that you're actually close. So that's.
Okay, that's very good. Thank you. So that's actually finishing our regular presentation. We have got one more presenter. That's actually Mr. in the last session, I think, isn't it? So if we can actually stay another 20 minutes and give opportunity for